Welcome back to the Automation Podcast. My name is Sean from Insights, and I want to thank you for tuning back in. Now, in this episode, I had the pleasure of meeting up with Eugene Silva from Emerson to learn all about the industrial control and monitoring system that comes with their industrial dust collectors. Now, I thought it was very interesting. I hope you do as well. But before we jump into this episode, I do want to thank our members who made the video edition possible. So when a vendor doesn't sponsor the episode, the video becomes a member-only perk, and that is just $5 a month to get started. So thank you, members, for making the video edition possible. With that, I also want to thank our sponsor for this week's show, theautomationschool.com and theautomationblog.com. I have an update later in the show, what's going on both sites, and I hope you'll stick around and listen to that towards the end of the show. But with that said, let's go ahead and jump into this week's episode of the Automation Podcast. It is my pleasure to welcome Emerson back on the show and Eugene on the show to talk about dust collector monitoring. You guys can see the slide if you're watching, dust collector monitoring and control solutions. I'm excited about this because this is a solution versus like a discrete product. So with that said, Eugene, would you please introduce yourself to our audience?
Yes, Sean, thank you very much for this opportunity. Hello, everyone. Here's Eugenio Silva. I'm a product manager, intelligence automation within Emerson, the discrete automation part of Emerson. I'm glad today going to share some of our understanding and learnings with the dust collector monitoring control solution. And when I talk about that, Emerson is also involved in other types of solutions that our purpose is to drive innovation that makes the world healthier, safer, smart, and more sustainable. And I'm also responsible for continuous emission monitoring, dust collector is this one, utility, energy, and compressed air management solutions. So for today, I prepared something that we go a little bit into why this type of dust collector solution is important from understand of our customers and industry point of view. We're going to look into the fundamentals of dust collection, from the particle sensors to the dust collector systems, and then dive into the dust collector solution, where I'm going to provide you some features, also explanation why they are there, and how this kind of capabilities deliver value to our end users and customers. And hopefully to have time as well to have a short recorded demo that brings us full scope how the operators look into that solution when they use it. In terms of key applications, industries use cases, dust collector is essential for many industries that produce dust, produce any kind of a pounder, any kind of a fume, and typically air pollution control, pounder processing, handling, industrial dust fume ventilation are covered by one or another way by dust collectors. And the industries that I put in bold, these are the dirty ones in the sense that they produce a lot of particle, either in terms of gases or dust. Therefore, the regulations that are in these industries are quite strong. So cement, metals, chemical, plastic, carbon black and toner, like lithium battery, assembly, disassembly, metal foundry. And what is interesting is either you produce a waste that you have to manage it properly, can be also recycled, for example, in the industries like plastics in food or wood. All the collected dust that you have, you can also reuse and sometimes recycle. But why? Why this is important? Why is it important to extract dust from these industries? Let's start on the right side, because this is what the customer is looking for. Because the costs of pollution, the hazards, the safety accidents that can be caused by this kind of harmful airborne and particles and fumes are so substantial then of course is very much regulated in all these industries. And if you calculate the costs on the public health, sometimes big accidents in plants where even big fires or hazards to people operating the plant, we talk about billions per year, the cost of that. And one of the consequences of having such issues is that when the dust extraction system is not working properly, or you have really a downtime. For example, I'm going to explain that this really depends on components that are very, they use so often that they wear down, like filters, like pulse valves. And each time that we have a downtime, is not the cost of the dust collector downtime that's important, is the overall downtime costs that imposes to the operation of the plant, because in order to be conformist, they have to stop operating until they fix the issue. And these downtimes, of course, varies in many ways, in different aspects. How complex is this dust collector? But I'm going to give you some insights that if a dust collector system does not have any solution to monitor in real time or control the efficiency, basically the personnel is managing these assets without any insight, and everything can go wrong. That's why the TCO and the maintenance aspects are quite important, because if you're not aware where is the problem, when you have to plan, and this becomes a firefighting or reactive mode, then your costs are going to be quite high. And when you talk about TCO, it's about the cost of the equipment, the acquisition, the cost of operation, meaning not only the personnel, but in this case, we use a lot of compressed air. I'm going to explain why. The maintenance costs, as we explained, and the disposal costs. Disposal means the filter bags that must be replaced and change, but also the dust, the fume, all the elements that must be properly managed and recycled sometimes. So this is the aspects why it's important. Now let's turn about the benefits and savings. So if you use dust collector solutions of any kind that can monitor in real time all the aspects of the operation of the dust collector system, and also contributes turning maintenance from reactive to preventative and maybe predictive, then the best thing that you can do is to avoid huge penalties. As you can see on this graph, every decade, let's say, the fines are getting steeper. And the reason for that is because the damage and the result of a big, let's say, issue on the plant regarding to this dust part is quite heavy. So therefore, we talk about 100Ks or even plus in some industries like primary metal and chemical, where one single incident, it's about 100K in average or more. And then, of course, to avoid that and to be completely compliant, you have to operate that systems in many cases 24/7. And therefore, any way possible to reduce downtime, and as a plus, reduce the energy costs, because for compressed air, you have to use electricity, then it pays off, because you're going to be full-time compliant. And the other thing is, if you do properly monitor and control your dust collector system, you also increase the filtration efficiency. So that means you are far from the high levels where after that thresholds you would be penalized. You can operate under conformance, under compliance, but you can also expand the equipment life. For example, the life packs, the pulse valves, You don't have to replace as often, which is the case if you don't do any real-time monitoring diagnostics. On the left side, the way that we talk about improving maintenance is the total costs. When we talk about the filter life, at least one unit of a filter, it's about 18K US dollars. And you see that the tip of iceberg is just the purchase price. The dust collector system, of course, has an acquisition cost, but below that, as a total cost of ownership, you have the energy that you expend utilizing the systems. You have the filter bags. You have to keep parts in your inventory. You have to dispose of that. And of course, you have the downtime costs and also the labor costs. Now I'm going to just give a chance to say, okay, tell me how a dust collector system works. And these are going to be general principles and basics. In general, a dust collector system looks like this. It's a unit where the air is pulled in at the bottom of the compartment, and this could be forced or not, and then the air gets out on the top, the outlet, and the dust is collected on the outside of the bag. So if you see this in this picture, we have one full bag in kind of light brown color with a specific fabric, could be porous fabric, PVC, or some even paper in some cases. And then the clean air exits at the top. And what happens is that the dust cake builds up on the bags, on the outside part of the bag. And if you see the number 1 on top, in that particular entry point, we have two pulse valves with compressed air in order to shake a little bit these post bags, filter bags, and then knocks down the dust out of these bags. And then they are collected by a hopper at the bottom. Okay, so that's basically, in general, how it works, the principle. It's a bit more complicated. Here is just to show that in order to automate a dust collector system, including the filter bags, we use a combination of electrical and pneumatic components. And these are from pulse valves, the ones that continuously blow air into these pipes. The compressed air tanks that hold the right pressure and the right compressed air capacity in order to keep the filtration efficiency very high. Then you have the filter regulators that you have to bring the pressure of this line to higher enough to be efficient, but not so high to spend too much compressed air. Then you can use controllers, black boxes that are able to do a time-based sequencing, but these are not so much sometimes efficient because it doesn't take in consideration all the diagnostics that you can get out of it. And then basically the very important element is this particle sensor that is on the outside of the clean air, because that is going to be your canary in the mine, right? It's going to be the one that indicates if the filter system is efficient, and if the job is done right. And then the other things. But let's go back to a very interesting view. You remember this picture here that you're looking at a cross-section of the dust collector. Now you could imagine how it looks like from the top. From the top, it looks like that. There is a compressed air tank that covers a certain portion of the filters units. For example, it's very common that a filter, complete filter unit might have different compartments. And in each of these compartments, you have a series of filter bags. And then imagine that you provide short but very powerful pulses of compressed air that are periodically injected on top of these um, columns. And below there's a filter bag, so therefore they are going to expand a little bit, and the dust cake then outside of their surface follows. And by inertial forces, of course, this dust is accumulated at the bottom, which is extracted into a hopper. Of course, now depending of the number of the filters per line, per row, this pulse valves needs to pulse a little bit faster or not. And the interval time, if you just follow time-based approach, could be 3 to 6 minutes. Now, if you calculate in the average filter unit, you may have 12 of these filter bags. You can have about 7 to 10 pulse valves per unit. It's very common that one large installation would have about like 500 pulse valves and 4-6 times more filters installed. And imagine that if each of them having pulsed every 3 minutes, 24/7 during 7 days a week. So can you imagine the amount of compressed air that can be spent? That's why these pulses must be very short and powerful in 100 milliseconds to avoid it also big waste. I think that picture on the left side just simply say that it's a lot of interesting things to get the dust removal, but basically is a jet of compressed air on top that shakes the filter, and then by gravity, the dust cake is removed.
It's not just a filter. I think many people may just think, well, a dust collector is just this bag that catches all the dust. You're actually, um, you do have the bags, but you're using compressed air to sequentially, depending on how many you have, shake those bags in a sense by blowing air into them to shake off the dust so it falls into the hopper. And so you can definitely see, like you were mentioning, if you have lots of these cylinders or these bags, then the sequencing has to be, pretty precise and pretty repeatable to make sure you're cleaning all of the bags off. And I'm assuming too, you need to know when the hopper's full because everything stops working if the hopper gets over full. So very
Yes.
interesting. I think your diagrams do a great job of explaining it as well.
Yeah. And I play a little bit when I mention that. It's a little bit the reverse way of our vacuum cleaner, right? Because
Yeah.
we suck the dust inside of the bags.
Hmm.
And when the bags are completely full, clogged, the suction power it's far reduced, right?
Yeah.
So then you have to empty our let's say filter bags. Here is although the all the dust is accumulated on the outside, the outer surface of the fabric, but the
Hmm.
effect is the same. If there's so much dust on the surface or out of the surface, then the air that is shown here, the intake, the dirty air, and then the filter air simply stops. That's why it affects completely the efficiency of that unit. And the post-jet cleaning is a way to unclog or to clean the filters in order to bring them to the more efficient operation.
Yeah. Especially if you have lots of dust, you need an automatic way to continue to clean it and get it off of the filter and into the bin. So yeah, no, that makes a lot of sense.
Yeah. In other cases, although you're talking about dust, of course, it could be any kind of a pounder. Like, for example, in the foods and beverage
Hmm.
industry, you don't want these, or for example, let's say a dry milk production. You don't want that dust to be floating around because it can bring contamination. But
Hmm.
believe it or not, it can ignite a fire
Yeah.
sometimes. So that's why it's important to get that completely eliminated. So this is the part that very people would say, okay, on the outlet where the air should be cleaner, as you can see on the right side, that this particle sensor is located at the outlet clean air side. It has a very interesting, the way it works is quite interesting. We use we have a sensor in our portfolio called P152 that we take advantage of this triboelectric effect. Basically, this sensor is coated with PTFE or a Teflon layer, so it's completely electric isolated from of course, the media. And then when the dust starts touching that probe, ADC charge is transferred. But because this sensor probe is completely isolated with a Teflon layer, the resolution and the electric charge is in the order of a picoamp, so 10 minus 12. And the resolution is about 0.5 picoamp. So therefore, if you're touching the particles, depends of their size, they are going to generate more or less electricity that's going to be transferred. And the ones that are just surround, they are not touching. For example, imagine that this duct air exhausting pipe is quite big, a bit half meter, maximum 1 meter around that sensor. The particle also generates induced charge in AC. And by measuring that, we have an idea about how clean is, of course, the air that's getting out. But it's a bit more tricky than you can imagine because it looks like this. Every time that you use the jet pulse with the pulse valves on top of the filter bags, it creates a peak. So that means the cleaning cycles that are happening in a duration of just 100 milliseconds, that's why they are very, very thin. And they happening every 2-3 minutes per row. They have in nature a little bit of noise, because imagine that every time that you clean, more dust gets inside of the filter bag. So that means it's like when you clean your vacuum cleaner, immediately when you turn on that, some of this dust is gonna get inside immediately, and that's the peak. But now imagine that you have a rupture in the filter, or you have a big roll, because unfortunately the things are wear out. And then this peak starts getting higher and higher. So therefore, what we do when we put that solution in place, for a little time, let's say a couple of days, we needed to kind of set up these thresholds. We need to figure out the level of noise that could be, because it depends very much the capacity, the types of a dust. But once you do that, in our solution, we set the thresholds like a warning alarm, which means that after that point, the maintenance crew starts looking at that could be an early indication that a filter bag is not okay, until the maximum point that avoids any non-conformance issue, which is already a rupture. You really pass the time where this filter must be replaced.
So we're looking at this chart for those who are listening, and the particle sensor, it's measuring the particles as the air flows normally. But during the pulse, right, we're forcing a lot of air back down. So we're getting a lot more, than the average air would have X amount of particles. But if we're forcing a bunch of it back in, we're going to see a lot more particles per, let's say, 100 millisecond pulse, right? So we do expect a peak when we pulse it, because we're just forcing a lot of air back, going the reverse direction. so we can shake the
Exactly.
bag loose. But what you're saying here on this chart, I find so much interesting. So you can quantify like the expected increase in dust that you're going to sense with the sensor when you go in the reverse, when you pulse blow the air downwards to shake the bag free. But you're saying if that extra increased amount of detected dust is either too high above normal or too low below normal, then that tells you that you could either have a clogged bag or you could have a burst bag. Am I understanding that correctly?
Yes, this is correct. And then the interesting thing is that as soon as you're getting closer to replace a filter bag,
Hmm.
this baseline starts raising a bit with a kind
Oh.
of, how can I say, there is a drift. Why? Exactly what you said. A filter is completely clogged. It's not yet any rupture, but the efficiency of the cleaning is
Mhm.
not so okay. So therefore, this slightly changes needs to be analyzed. Why I'm showing row 1 to row 10? Exactly in the picture, if you remember, a compartment filter with several, let's say, filter bags,
Mhm.
they are under the row. So under the row 1, you may have 10 filter bags, row 2, row 3, and so on. So that means you are able to indicate which row is the problem, but it might be that you still need to check further which of the filters in that particular row have the problems. The more quick this peak happens, more number of filter bags can have a problem.
Mm.
Okay?
So you have one sensor on the exhaust, and you're sequencing through, blowing out or shaking out, pulsing each of the rows. So that's why we see, one reading across the horizontal, and we see your row one, row two, row three, row four, each of them with discrete values or pulses. And like you just said, if you have multiple issues on a row, then you're going to see, a higher or lower peak depending on what the issue is. I'm with you.
Yes, that's why I'm going to show the other diagnostic capabilities that
Okay.
we need to associate with this particle sensor. And just to remember that this particle sensor, we simply use one unit on
Hmm.
the outlet part. That's why I needed to make the sequence
Hmm.
in serialization of the pulse, because then I need to synchronize with the pulse jets of every row.
Hmm.
No? Row
And I
1,
think
2,
too, if
10.
you tried to do them all at once, the you would need a lot higher pressure. So it kind of makes sense to do it row by row because it reduces your maximum pressure required.
Yeah, in this particle sensor, you not be able to
Differentiate, yeah,
identify which of the roles would be the
had the
problem.
issue.
That's why we kind of
Yeah.
still have to do that.
Hmm.
But now let's give a solution overview. And I think that some of the key capabilities and features are going to highlight even more the other diagnostic capabilities that we are able to provide in order to identify correctly and early as possible such issues. So this is a typical dust collector system.
Hey everyone, I hope you enjoyed this week's show. I know I really enjoyed it. And of course, I want to thank our members for making the video edition possible. So, this vendor did not sponsor this episode. So, the video edition is available for members, and there's some great graphics in their presentation you guys may want to check out. Now, with that said, we do have some really exciting podcast episodes coming up. I'm sitting down with Inductive, I'm sitting down with Software Toolbox, I'm sitting down with Siemens, and a bunch of other vendors. So, we have plenty of new podcasts coming up in the coming weeks this summer. And I also wanted to give you an update of what's going on over at the Automation blog. We've had some new articles come out. Brandon Cooper, one of our freelancers, wrote a great article about emulating Allen Bradley E3s. We had a vendor actually submit an article and sponsor the site to submit an article about what makes a good automated palletizer. We also had an update about the Automation Museum. That's a fundraiser we're running. We're trying to open an Automation Museum. I got a lot of legacy stuff I'd like to donate to it. And I'd love to have it so you can come in and actually walk through, not just see the stuff, but actually learn on it, right? So maybe you have some old stuff in your plant, you come out to the Automation Museum and you can learn how to use it. With that said, we're also looking at possibly doing a podcast for Automation Museum to drive awareness of legacy automation. So So any of you out there interested in that, contact me directly. And you can do so over at theautomationblog.com. Just click on the contact button. And we also have two articles from Brandon Cooper about things he learned as he transitioned from working in a plant to traveling around and visiting other plants to help them with their processes and automation. So check those articles out over at the Automation Blog. And finally, over at the Automation School, we have the new Factory IO courses. We also have, I just added a new lesson to the Logix version of that course. Somebody wanted to try to use bit shifts instead of counters, so I added a lesson on that. Plus, I'm now starting to update all of the courses, including the brand new ones I'm working on. So you're going to see a brand new Start Here lesson later in the week. And I'm working on some cool emulation lateral logic for my PLC courses that if you don't have any push buttons or limit switches, you can actually use this code I'm going to give you for free to simulate the widget machine that I use as kind of the basis for my teaching. So in any case, check that out if you're in one of my PLC courses over at theautomationschool.com. And with that said, I'm very thankful for all the vendors who come on, especially those who sponsor the episode so I don't have to do these commercials. I'm not a big commercial guy, but I do want to thank you for hanging in there and listening through this update. And now we'll get right back into this episode of the Automation Podcast.
And if you look it around, if this dust collector system is just, let's say, automated with pneumatic electric components, and they don't have a real-time monitoring, you not really know the emission level. If it also this is not real-time monitoring with some diagnostics, then you're not able to identify when this particle sensor, for example, is completely taken by the dust because the humidity entrance in that pipe, or it might be that it's so dirty your dust that is already ingrained so much on the probe. Mm-hmm. So that's why the poor reliability or the low level sensitivity of that could be affected. And if you are not monitoring these signals that I showed, these peaks synchronized with the pulse valve jets, mm-hmm. you don't have any early warning, okay? The pulse valves basically are coils. There are solenoid coils mm-hmm. with diaphragms that open and close at the speed of 100 milliseconds. The point is that their lifetime is about a couple of millions of cycles. Mm-hmm. But imagine, in some cases, 1-2 years is already enough to have end of life. So a fault valve has to be connected to a control system because you need to know if this is a short circuit mm-hmm. or if the diaphragm is completely open. And you can only do that if every time that you cycle the valve, you also check that. For example, the power that you drive the coil mm-hmm. gives you a feeling if that is a coil that is already gone, okay? Now let's talk about the compressed air, right? If you have a filter that is open, there's a rupture. If you have a diaphragm that's completely gone open, you start consuming higher and higher the compressed air. The point is, this is continuously increasing. You can just imagine that this is normal. But if you go into average and look at this in a historical way, you're going to see that this trend is caused because of the broken pulse valves, for example. So that's why it's also important aspect of the automation solution is to minimize the usage of the compressed air, is to have a clearly operating under a baseline that is normal. The filter bags, independent of the materials, because if you talk about life sciences, food, chemical, or metal, they have a different materials, they have a different wear out lifetime span. The point is, the costs might be the filter itself is not so expensive, but going up there, exchange, stopping, moving things around, getting the dust out before you change, putting all the personal protection equipment may take hours. So therefore, that is the cost of that. And if you're not able to prevent or even have an early warning when that is going to occur, there's going to be a reactive maintenance issue, right? So that's why just convincing that it's worth looking into different aspects. And that's why on the left side, when we talk about solutions, we talk about the connectivity part that we have to work with devices that are hard or 4 to 20 milliamps. Some of the devices are Modbus TCP, newer actuators and pulse valves could be MQTT or even OPC-UA. That's the PLC part that we have, and we can work with pneumatic systems, for example, that Ethernet IP, Profinet, or any other standard. Then, of course, we have the IOs that we have to look at to control the post-jet systems, but also to monitor the differential pressures, to measure the compressed air in some cases, until the part where at the top we put a HMI SCADA software platform that we pre-engineered in order to make it simpler, the development of that solution by our OEMs, or many cases directly to our end users. And all in the right are the elements that we offer in our portfolio. Some cases, OEMs of dust collector systems just to take from us, and they might be that they have their own solution as well.
So just for the audio audience, I know we've covered these products a lot, especially on the news show. But I mean, I'm just want to kind of go through a couple of these things. You got the ASCO product line, right? So remote piloted valves and, all of those, that category, the pulse valves. But we also got the Adventex, which we've talked about, like filter regulators and
Mm-hmm.
different cylinders. Topworks, which I think we're all familiar with, proximity sensors and whatnot. And some of the other products you guys, Rosemount differential pressure transmitters. We also see we have the pack systems. In this case, you could have Edge Analytics, and so you may have one of the pack systems Edge IPCs. And we even see the down in the corner there the Emerson PLC and IOs, which I think we're all familiar with as well. So that kind of shows you how, this solution, they're taking all these different products they have in their catalog and putting it together in one solution, which is, you kind of need all this stuff, basically understanding how it works. We just went through it. Um, and so it's interesting. I don't think I've seen a slide yet from Emerson where they kind of include in one application all, if not all, many of their different product lines. And then the skate on the top, it looks like just some beautiful screens and charts and dials showing the current status. So I didn't mean to interrupt you, Gino, but
No, thanks
I
for
just wanted to say
highlighting.
that, especially since the people listening, they'll be familiar with all those trade names because we've covered those in the past. But in any case, let me turn it back to you.
No, it's thanks for highlighting. And I say that when I introduce myself, that I'm from the discrete automation part of Emerson,
Hmm.
because most of people would know Emerson by the Rosemont, for example, pressure,
Mm,
uh, Fisher valves, and then
yeah,
the Delta V DCS, right?
yeah,
This is
yep.
the discrete automation part, and that's why probably something new for everybody here. Thank you very much. So when I look at that in a nutshell, uh, we of course have to put the sensor devices, the PLC on top, the HMI SCADA,
Mm,
and basically what we provide is real-time monitoring of these particulate emissions. We detect, but also locate where the leak is by compartment and rows. You can see on the picture that on the top of this HMI screen, we have a filter unit with 3 compartments, compartment 1, 2, 3, and each compartment has these rows on top, which is the number of rows, then a number of filter bags that within each compartment. So therefore, just locating which compartment and which row you have a problem,
mm,
I can tell you it saves half day of people in the maintenance. We also optimize the post-jet cleaning. It's an patent-based algorithm that is completely adaptive and works not just with the pulse valves, but we put head pressure sensors, and this fluctuation in the differential pressure that we measure from the outlet and inlet allows us, of course, to increase or decrease the frequency of these pulse jets, which allows not only to be more efficient, but also minimize compressed air. And then finally, when you talk about solenoids involve diaphragms, these ones we can indicate one by one where they have problems. So therefore, if you look at down to the other HMI screen, there are two rows on top. The one that is a solenoid, the one that is a diaphragm, and these vertical bars are the filter bag health. If they are getting closer to red with high levels, meaning that their lifespan is already gone. And if you have light indicators on the solenoid, the diaphragm, depending of the color, might be that you have a short circuit, fail, open diaphragm, therefore you have also to replace. And basically, when we install that solution, sometimes our customers ask it to also integrate with their control systems. So therefore, the compressed air generation, the fan, the hoppers, the safety alarms of the plant sometimes are fully integrated as well. Now let's talk very much about few features because these are the ones that probably you haven't seen yet. I want to talk about our HMI control system. Is based on Movicon Next platform, and basically it provides everything that you know from the SCADA HMI, and that's why we use this in general for applications like OIE, energy management, and some others, infrastructure monitoring like smart cities, wastewater facilities, solar mega plants, etc. Of course, it provides data visualization, but I like to highlight that you could ask, we provide connectivity to all major PLCs that you can imagine with communication drivers. Of course, the open standards like OPC, UA, like Modbus. And on the lower part, the green, let's say the gray part here is what we used for that solution. Sometimes we use geomaps to indicate where the filters are. Some georeferences, let's say geofences as well. The people have to be with a personal protection equipment to be there. So there are some real-time data that, of course, we are collecting for the particle emissions and other elements like differential pressure or header pressure. And then you have the headlines. You can see some screens that are completely dedicated to alarms and alerts. And one of these diagnostics that you see are related to the solenoid, to the filter bag, and to the diaphragm diagnostics. A lot of them are diagnosed in different ways. For example, the solenoids, we look into the power output of our I/O cards to see if the valve pulse, the solenoid is open or complete short circuit. The filter bag, I already explained it. We detect with some logic with the particle sensors. And the diaphragm diagnostics is based on the header pressure, because if this diaphragm is completely open, the differential pressure within the chamber, it starts fluctuating, and then you know that there's something wrong there. But all of them increases the filtration efficiency, changes from reactive to predictive maintenance. Of course, keeps the site compliant, minimize dust emissions, and for sure increase equipment lifetime, like the filter units, and reduce the compressed air usage. If you sum up all of that, the return on investment it might be quite fast. Of course, for large installations, might be within 2 years, but it's still a very fast return on investment for that particular solution. That's what it looks like. A little bit, let's say, zoom in. You see that they're not nice looking, but they indicate graphically where the issues are, the number of issues. On this screen about thresholds and alerts, the second one on the right side, is like the number of cycles. Imagine that every pulse valve would have about a couple of millions of cycles of lifetime. Here you can at least predict when or how many spare parts that you need to have in the next quarter. And then the yellow or red signals means that red gone, you have is a faulty, and the white ones, or the yellow ones are the ones that you need to watch because they're getting closer to the lifetime, dead of lifetime. The other aspect is, like I said, when dust collector systems, you acquire that without a solution, it comes with this sequence box, which basically is a time-based pulsing. So it keeps pulsing 3 to 6 minutes, like I said, 100 milliseconds, but it can change. It's fixed. And that means that leads to an excessive use of the pulse valve. So you're going to wear out quite sooner than it should, but also reduce the valve bag life because stretching the bag filters, of course, you're gonna also wear out, and you waste much more compressed air than probably you should. That's why we implemented these other two types of post-jet cleaning methodologies. One is on demand. That really depends on the high differential pressure between the chamber, and you can set in the solution how these multiple filter lines are going to operate normally, and this differential pressure threshold can be, for example, when the efficiency is getting bad, the differential pressure gets lower, and then if that is within a certain band, you can estimate that there is accumulation of the dust cake. The other one is very intelligent, is a function block in our PLC that does a dynamic change. So therefore, you put a single set point, and the adaptive algorithm, based on diversion pressure, starts controlling the intervals between the pulses. So the idea is that to optimize by eliminating unnecessary pulses in the cycle of these valves and also minimizing the compressed air. Of course, when you install the solution and you put the set point for the first time, the system needs a little bit time to learn, and it's a learning algorithm that starts adapting, and very soon it starts performing optimally. Okay? And that looks like that. This is just another possibility to see. You see that on the left side, you see a particular rows, and each of these rows have the filter bags. Mm-hmm. Each filter bag has a vertical bar that indicates the healthy of that. Solenoid diaphragm is on the top. And then each of these compartments can navigate from one to another. Then you have other additional elements like the header pressure, differential pressure, particle density, and you have a trend diagram that you are able also to generate reports, but you also to monitor in order to tighten a little bit the parameters in order to be more efficient. And then on completely right side, if you have more than one dust collector, you can create different screens if you want. But the idea here is that the C1, C2 means compartment 1, 2, 3. Again, the diagnostics that leads to preventative, predictive maintenance and avoid completely reactive maintenance. Interesting, if you don't know, in order to replace a single filter in order to check if a solenoid valve is completely short-circuit, in order to see if a diaphragm valve is open, you need to get there in this personal protection equipment using mask, gloves. You need to go up. You need to kind of get to know where these things are. And imagine that if you could avoid and just look at the screen and say, hey, I know that this is the compartment 1 of the filter A, and I know where I need to look at. And by the way, I have the spare part because I had early indications to fix it. So then we are not just talking about reduction time, but I guess reduction costs, and avoid to put people every time in such a very interesting environment. Okay? I'm not going through the right part because you can imagine that this is a description of how things are usually done. And if you turn this around into a proactive predictive maintenance, then you have less and maybe faster steps. And you can prevent and can plan in advance when you want to go with these units and you have to wear this equipment for protection. So very quickly in the value proposition. Of course, like any solution, customers are interested to know if they can pay back very quickly. So the return investment of that. So that's why we check the size, the number of units, what's the minimum size the customer could start with, because it is a pre-engineered solution, how fast it could be that we implement in the whole site. It could be also, of course, calculate how much their current expenditure in terms of maintenance, reactive maintenance, the cost of utilities like compressed air, how many times they have to, or they have downtime issues. And from that, we can prove very quickly, very simply that it's worth investing in automation. 20 to 30% of our reduction is a lot if you consider that they use a huge amount of compressed air. And compressors, they use electricity. So therefore, if you're able to reduce compressed air, you also increase your operation efficiency because cost of utilities is one of the points. Downtime is everything. Maintenance, it's about preventing that you need to do these manual inspections. Just go there, check, and come back, and you see that, okay, we could wait for another week, but because I'm here, I'm going to change anyhow the filter. And that, of course, you're not increasing the lifetime of your equipment. And interesting that some downstream equipment, like the blowers, like the vacuum pumps, if they get a lot of dust or excessive dust, they also damage them. So therefore, maximizing maintenance, optimizing every step pays off in that sense. And finally, of course, customers do that because they want a full compliance. Every possible issue can be tracked, can be reported. The efficiency of the systems can be audit-ready reports. You can really prove that you are reducing particle emissions. You provide a lot of visibility what's going on. So therefore, the technical teams are in very high confidence to operate the system, because if without, they are operating blindly. And that's why they feel a bit concerned many times that might be that bad things are just going to happen. In a nutshell, we talk about savings, extending the filter life. We talk about savings, reduce the compressed air. We can avoid downtime. Each downtime is one event that costs not only in the maintenance part here, but also the whole production costs that are not calculated here. And half the penalty is that if you have a single issue, it's going to be a big one. So therefore, it's a good way to give customers an idea why they should invest the CAPEX part and how we can help with the OPEX to save their budget in the sense of operating dust collector systems. So, Sean, if I have time, 3 minutes, I'm going to run this HMI demo because then you can see on the screen how the different screens are operated. But it's up to you if I need to do that.
Yeah, go ahead.
Okay, so this is an HMI demo, of course, simulated here because imagine it's not possible to connect live or to have all this whole equipment. So then I'm going to click here. So basically you see how a operator would navigate, the type of information that is provided. I made this click through very quickly because then we don't have too much time here, but you see that you are able to trend the particle density, the air consumption. You can set the alarms, you can indicate which pulse valve is not okay, how is the level of filter bags, and now the settings, the cleaning. These are the parameters that you can adjust. Like I said, we have an adaptive learning algorithm, but in many cases you need to at least set up. The sensors as well, how sensitivity of that. There are many different thresholds. And then the diagnostic part for the diaphragm and the rupture where you can detect. And once this is done, you can see that you have quite interesting information. For example, if you change the valve, you reset the counter. These are the alarms that you can acknowledge, etc. Okay? And that's it. That was the case.
Yeah, that gives you a good idea of what you're getting as far as the HMI is concerned, and it's good to see a full screen. I mean, it looks like a very well designed HMI. From my perspective, it looks like it's really giving you, it's focusing in on any errors. So you have like just standard graphics, very good looking graphics, and then if there's an error, you see it in red or yellow. Really calls the eye to it. But Eugenio, I see that there's a QR code on the screen right now. Can you tell people where that goes?
Yes, it goes to the product page on our Emerson.com site. And from there, you can request for demo, you can request for proposal, you can request for more information. So this is the entry point for you to get to know how we provide that solution, which kind of basic elements. And there we have also the related product pages if you want to get to know more.
And I think the important part here is a lot of times you know when you have a dust collector system that is constantly needing care, right, to keep you in compliance and make sure your products are being made correctly and you're keeping people safe and all of that. Um, these systems they're gonna be expensive, and larger systems, of course, are gonna be expensive. And so that cost savings, it's like energy savings we do with VFDs on pumps and fans, right? Or energy savings we do when we're doing lighting. The folks over at Emerson are going to want to help you kind of quantify that because, they know that for you to be able to justify not only, hey, this is giving us a lot of problems, we know it's costing us money, you also want to know your ROI, right? And so they're going to work
Yes.
with you on that because that's on these big projects. Those are some of the things that we have to look at to be able to, the budget correctly. Anybody who has ever been in the budgeting part of a company knows you just
Yeah.
don't spend money because it's fun. You have to have a reason behind everything. So I would guess I'm right on that, Eugenio.
Yes, and Sean, although I just covered the technical part, of course, without any commitment, we can talk to customers and consult then
Yeah.
to look it around and see in terms of maturity, how they operate these dust collector systems. We can, of course, check the install base. We have a questionnaire that they can fill it in. We can understand the size. We can, for example, talk about the energy consumption, the number of hours that they are spent on reactive maintenance. And based on that, we give them an opportunity to analyze whether they want to invest in that solution, which is a CapEx investment, but also we prove how much reduction they could have on the OpEx part.
Yeah, which is how they're going to justify it. Well, Eugenio, I want to thank you for going through that. I really enjoyed your presentation. I learned a lot more about this product line and actually this product category than I knew coming in. And I think you did a great job of walking us through it all. So thank you very much for coming on the show.
Sean, on behalf of Emerson, we appreciate this opportunity, and it's my first one here, so I also enjoy it, and this was great. A great conversation, great questions, and thank you.
Well, I hope you enjoyed that episode. I want to thank Eugene for coming on the show and bringing us up to speed on dust collector systems. I really didn't know all of those technical details, and I really appreciate him going through that. And it's cool to see how they integrated so many different Emerson products into that solution. I mean, it's just not like a PLC and some I/O. There's sensors. You guys saw it. I'm not going to go through it again. But in any case, really appreciate that. And I also appreciate our members who made the video edition possible. Thank you, members. Your $5 a month not only unlocks this video, but so many other videos that we've done, hundreds of videos I've done over the last 12 years. So thank you for being a member and supporting my work. I also want to thank theautomationschool.com and theautomationblog.com. I hope you guys listened to that update that I included in the show. So many good things happen at both places. I hope you guys will take a moment to check out both websites. And with that, I just want to wish you all good health and happiness. And until next time, my friends, peace.